Good afternoon. So first of all, I would like to thank the organizer of this QMAT for inviting me and allowing me to present my work. So today I will discuss the results of one of our recent work titled Correlated Low Temperature Dynamics in a Stretched Diamond Lattice System YB-NB04. I am Kaustav Mukherjee from School of Physical Sciences, IIT, Mandi. So the plan of my talk is that first, as usual, I will give a brief introduction related to my talk. Then I will define the objective of this study. Then I will discuss the result obtained. And finally, I will summarize the work. So over the last couple of days, a lot of discussion is going on about frustrated magnetism. The word frustration is known to all of us. It's a condition when we do not know what to do. In life, certain times comes that we don't know what to do and hence feels frustrated. Now, how that is related to spins? But this is one of the very important topic nowadays, that frustrated magnetism is a keyword in various journals and lot of investigation are being carried out. So basically, if I start or this topic, so the first thing which come is that what do you mean by magnetic frustration? Okay, the magnetic frustration is nothing but is a condition when the spins are unable to satisfy all exchange interactions. Now, as said by many speakers in other sessions, the frustration can arise either due to geometric frustration. So, what do you mean by geometric frustration? That you simply consider a triangular lattice. In one of the vertices, spin is pointing up. In another vertices, spin is pointing down. What about the spin which is in the third vertices? Whether it will point up or it will point down. Hence, it becomes frustrated. So, this is one form of frustration. Another form of frustration is that due to competing exchange interaction, frustration can also arise. So, what do you mean by that? It is a condition when the nearest neighbor interaction, suppose J1, it is competing with the next nearest neighbor exchange interaction. Okay? And this condition can arise in certain lattice geometries. Okay? Now, to quantify this frustration, a frustration factor was introduced, which is nothing but the ratio of the QoS temperature and the magnetic ordering temperature. The QoS temperature, as we all know, that can be obtained by fitting the inverse susceptibility versus temperature curve and with a QoS law, and we can get CW, and Tn is the ordering temperature. Okay. Now, generally in literature, if F is greater than 1, a system is said to be have some frustration, but for condition when F is much greater than 10, the system is said to be strongly frustrated. Now, why all this frustration we are all discussing over last 3 days? So, what happens if a system is frustrated or a magnetic system is frustrated? So, the first condition is that in a frustrated magnetic system, long range ordering is suppressed, but it does not imply that the system become a non-magnetic system. Due to suppression of this long range ordering, many novel magnetic phases evolves, like spin liquid phase or a spin ice phase or effective spin half state, etc. Okay? So, all these novel phases are worth investigating. Hence, this magnetic frustrated system become important. Now, the next question is to where we should investigate these things. So, it can be generally investigated in frustrated magnets, and quasi 2D magnet, 3D magnets can be a part of this frustrated magnet. Why I am saying that, using the term quasi? Basically, quasi means that in those systems, the properties mimics that of a 2D system, but they are in a 3D lattice. Okay, so there are some examples of this quasi 2D system can be triangular lattice. So basically what are these triangular lattice? They are nothing but they are S-sharing triangles, and a very common example of such triangular lattice is YMGGAO4. Another this 2D lattice which has been extensively investigated is this Kagome lattice, which is nothing but corner sharing triangles. The effect of frustrated magnetism has also been reported in various square lattices, where various phases like spin nematic phase, then spin liquid phase, canted antiferromagnetic phase, etc. are all reported in square lattice. Now coming to this 3D lattice, the pyrocoals are the best examples of a 3D frustrated lattice. So what are these pyrocoal lattice? Basically, they are this corner sharing tetrahedra, and why they are important? Because they are a good potential candidate for spinized system. One of the example of this pyrocoals which are system which has been extensively investigated is R2 TiO7, and many others are there. Another form of this 3D lattice is the Kagome lattice, which is nothing but a corner sharing triangle in 3-dimensional. Kagome was corner sharing triangle in 2D, Kagome is a corner sharing triangle in 3-dimensional. And these lattices are, even though not extensively investigated, are good candidate for 3D spin liquid system. And another form of 3D lattice is the diamond lattice. Why we are calling it is a diamond lattice? Because in such lattices, the atoms are arranged in such a way that they are similar to the carbon atom arrangement in diamond, and such lattices are a good candidate to study Heisenberg J1, J2 model. But as per literature report, these diamond lattices are rarely studied for rare earth system. Now, why did I mention this term rare earth? To see this, we have to just recall the origin of magnetism in 3D system and in 4F system. Basically, in 3D system, the orbital angular momentum is quenched due to strong crystal electric field effect. So, the total angular momentum in this system arises mainly due to the spin angular momentum. And also in this 3D system, the effect of spin orbit coupling is very small. In contrast, for 4F system, means this orbital angular momentum is not quenched, and the total angular momentum arises due to the combination of both the orbital angular momentum and the spin angular momentum. So in this system, there is a strong spin orbit coupling. In 4F system, crystal electric field also acts as a perturbation, and as we all know that 4F moments itself are localized moment as compared to the 3D moments. So in one sentence, it can be said that in 4F system, Coulomb energy, crystal electric field, spin orbit coupling plays a very important role in defining the properties of this system. So basically, it can be said briefly that the rare earth based system hosts a range of 2D and 3D frustrated lattice, and this rare earth system in such lattices are good candidate to study the topic of frustrated magnetism. Okay. Now, I have earlier mentioned that there is a suppression of long range ordering, and it gives rise to the novel magnetic phases. So what are the possible quantum ground state which are observed or reported in 4F based frustrated magnet? So one of them is the quantum spin liquid, which we all know is a highly entangled magnetic state where spins does not order down to the lowest temperature. Then we can get quantum spin-ized behavior in such system. Then there can be random singlet state, effective spin hub state are also reported in such system, and also we can have spin tunneling and spin relaxation effect. Now for all this thing, what are the signature? So initial signature is that at low temperature there is a no long range ordering is observed. Also there is a minimal effect of thermal fluctuations. However, there are quantum fluctuations, but these quantum fluctuations are rarely can be probed with our laboratory system, and for this we need some microscopic probe like mu-SR technique, which I will further discuss. Now, in my title I have mentioned the term stretch diamond lattice. So let's have a bit elaboration on what I mean by this term, this stretch diamond lattice. So for that purpose we have to start with diamond lattice. So basically a ideal diamond lattice has a cubic symmetry, and when there is a cubic symmetry the nearest neighbor interaction dominates, and when there is a nearest neighbor interaction dominates there is a chances of having the frustration is minimal and we can have a long range ordering. Now suppose the diamond lattice is distorted a bit and it becomes a tetragonal symmetry. Then there is a this next to next nearest neighbor interaction due to the bond length can be comparable with the J1, and so J1 and J2 can compete. Now further, if the symmetry is further reduced from cubic to monoclinic, then what happens is that due to this reduction in symmetry, this J1, in J1 we can have a long bond length and we can have a short bond length. J2 we can have a long bond length, we can have a short bond length. So what happens is that this due to this reduction in symmetry, due to reduction in symmetry, what happens is the diamond lattice becomes stretched or distorted due to this monoclinic symmetry, and compared to these two systems there are various JS interactions which are present, which are of comparable strength, and due to this what happens is that there is an enhanced frustration effect in this system, and this such stretch lattice geometries have been seen in some members of rare earth tantalates or rare earth neobate series. Hence, coming to this objective of this study, we chose YB-NBO4 for this work. Now, why YB-NBO4? First of all, it is a three-dimensional spin system. Next, YB is a Kramer ion, hence it is sensitive to both spin orbit coupling and crystal electric field effect. Hence, we prepared this YB-NBO4 compound using standard solid state ceramic route and performed the XRD. I have not shown the data here, and we did the Rietveld refinement, and it crystallizes in a monoclinic structure with space group I2 by A. And using the obtained lattice parameters from the Rietveld refinement and using the VESTA software, we made this structure of YB-NBO4. Here these YB ions are the green ions and are surrounded by 8 oxygen ions having 4 different bond lengths. Also these NB ions are surrounded by 6 oxygen atom having a 3 different bond lengths. So basically these structures have a distorted YB-O8 and NB-O6 polyhedra. And also in this structure, this YB, that is the magnetic ion, the arrangement of YB ions is similar to that of diamond lattice. However, this system is in a monoclinic symmetry. So due to reduction in symmetry, what happens that there is a deformation in the magnetic diamond lattice, and we get various bond lengths J1L, J1S of comparable strength or the comparable distance. So this is a stretched one due to this distortion. So we are calling this sublattice as a stretch diamond lattice, and in this stretch diamond lattice the magnetic interactions are of comparable strength. So this system is a strongly frustrated system. So in one sentence it can be said that this YB-NBO4 is a 4F based stretch diamond lattice and is a ideal platform to study the role of spin orbit coupling and crystal electric field effect along with the inherent frustration which is effect of inherent frustration which is present in this crystal structure. And also, as it's a three-dimensional spin system, so this can be a possible candidate for three-dimensional quantum spin liquid, which is relatively rare compared to other quantum spin liquid which are quite prevalent in two dimension. Now coming to the data. So as I mentioned that the fundamental signature is that there should be no long range ordering. So we did magnetization measurement as a function of temperature chi dc both in ZFC and FC mode, and what we see that there is no magnetic anomaly and both the curves superimposes on each other. We also did AC susceptibility measurement at different frequencies as a function of temperature, and as you can see the AC chi graph for all the frequencies are superimposing on each other. Now these two measurements were done up to 1.8 Kelvin. We further did a few chi-T and MH measurement at the ultra low temperature. So here we see that up to 300 millikelvin, what we see that there is absolutely no anomaly. It's a smooth curve which is rising. Okay. So from these three graphs, it can be said that in this compound there is no signature of spin freezing. Also, there is a absence of long range ordering down to at least 300 millikelvin. Okay. And here we at higher field we got some field induced polarization effect. So, but the main thing is that in this YbNBO4 long range ordering is possibly suppressed to a very low temperature due to this frustration effect. We also did a thermodynamic measurement down to 1.8 Kelvin which is shown here. So, this curve is also a smooth and there is no anomaly is observed, which is in analogy to our magnetization curve. We tried to fit this heat capacity curve using a combination of Debye and Einstein model. So, the data fitted well at higher temperature, but as you can see in the inset a upturn is observed and the fitting also deviated. So, this upturn is arising due to possibly due to Schottky anomaly, because what we saw and I will also show later is that under the application of magnetic field the upturn is changed into a peak and the peak temperature increases with the increase in magnetic field. So, to get some better idea of the magnetic state of this system, inverse susceptibility is plotted as a function of the temperature and it was fitted with Curie-Roess's law. What we saw that the curve fitted well, that is the red line fitted well above 120 Kelvin, but below 120 Kelvin a deviation was observed. But the obtained magnetic moment was around 4.6 mu v, which is almost in agreement with the theoretical magnetic moments of the Yb3 plus ion. Now here we see a deviation. Generally this Curie-Roess's law, if there is no long range ordering, should have been fitted in the entire temperature range, or if there is a long range ordering above the temperature range. But why this deviation is there? So this deviation possibly indicates that crystal electric field is playing an important role at the low temperature properties of this compound. So we tried to fit the graph using a two-level crystal electric field model, and here the obtained delta was around 330 Kelvin, and we saw that the graph fitted well from 120 Kelvin, 20 Kelvin to 300 Kelvin. Now this delta implies is the energy gap between the ground state doublet and the first excited state doublet. Now to get some better idea about this crystal field effect in this system, we did point charge based model calculation of this system to get a better idea of the crystal field scheme. Basically, point charge based model calculation is a Python is a first principle based calculation using Python based software, and here what is considered is that the cation is surrounded by the anions and the anions are considered to be a point charge. Okay, and based on that, from the parameter obtained from our crystal field Rydberg analysis data, we tried to fit it. So, but first we have to look what is the condition of YB ions at the high temperature. Basically, this YB ion have 13 electron in the F shell, and using term symbol calculation we found out the total spin moment as half and L as 3. So, J was calculated to be around 7/2. So, under spin orbit coupling what happens is that these levels are splitted into twice J plus 1, that is 8 degenerate state. And under crystal electric field it is we get 4 Kramer doublets of different energies, and what we found is that the value of delta obtained from this point charge based calculation was around 28.2 MeV, which is approximately around 327 Kelvin, and it is in a good agreement with the value obtained from the 2-level crystal field analysis of the chi-DC data. So, this indicate that, or this suggests that the low temperature magnetic properties of this system will be only depends on the Kramer ground state doublet, and this system can stabilize a low energy J effective half state. Now, below 20 K we try to fit the susceptibility data again with the Curie-Ross's law, and what we found is that the effective moments have a reduced value. However, we saw the literature and this reduced moment was common in other 4F based system due to the presence of J effective half state, and from here the Landé value was found out to be around 3.1. Now, to get some, only 3 minutes. So, anyway, so what we saw is that means we did the MH analysis, and what we found that the all this fitting using this Brillouin zone curve yields a Landé value of around 0.3. We also did MH curve at the 400 millikelvin, and we tried to fit it a Brillouin zone function which is generally used for a paramagnetic state, and what we saw that there is a deviation between the experimental curve and the fitted curve. So, it implies that the correlations are developed at low temperature. Now, we did the Schottky anomaly obtains a Schottky anomaly contribution to heat capacity as a function of temperature, and we fitted with a 2-level Schottky model, and all these values give a Landé factor of around 3.1, which is in good agreement with the values obtained from low temperature magnetization analysis. So, basically it confirms a J effective half state within the Kramer ground state doublet in YB NBO4, and such state can give rise to exotic quantum phases, and for that mu-SR technique is a good technique, and details about mu-SR techniques has been said number of times, or fundamentals of this technique have been said number of times by my previous speakers in different sessions. So, I will just show the data. This asymmetry versus temperature time curve at different temperatures is shown. From this figure you can see that there is neither oscillating component and there is no drop in the initial asymmetry. The curve is fitted with the stretch exponential function of this form, and the exponent beta is found to be constant. So, it totally excludes the possibility of any impurity or disorder induced relaxation. Also, what we see that there is no magnetic ordering down to 300 millikelvin because there is no oscillating component, there is no initial drop of asymmetry. Also, what we found that the relaxation rate below 2 Kelvin is found to be increased with decreasing temperature, whereas above 2 Kelvin it is constant. So, it implies that correlations are present below 2 Kelvin. Now, we also superimpose the longitudinal field, and what we saw is that the relaxation passes. So, it implies a strongly fluctuating nature of the internal field. So, we tried to fit this relaxation rate with the Redfield model and found out the fluctuation rate, which is around 228 megahertz, and it is comparable to other reported system having a dynamical ground state. Also, the lambda t is fitted with the phenomenological model, and we found that an accelerated down to 0, where we found a persistent fluctuating regime below 100 millikelvin. And also chi the relaxation rate was found to be vary as 1 by 3 between 300 millikelvin to 1.5 Kelvin, and such variation is observed in other quantum spin liquid system. So, it implies that in YbNBO4 there is a crossover from a paramagnetic to a possible quantum spin liquid region in YbNBO4. So, if I summarize, in YbNBO4 the magnetic ions are arranged in a 3-dimensional state lattice geometry. There is the absence of long range ordering and spin freezing down to at least 300 millikelvin. There is a presence of effective spin half state. There is strong magnetic correlation below 2 Kelvin, and the nature of the internal field is dynamic and not static in nature. So, it can be said that there is a presence of correlated dynamical ground state similar to quantum spin liquid in this system. So, I would like to acknowledge my present and current past students, and this work is mainly carried out by Jogender and Dhiraj, and also in collaboration with Dr. Nakamura in J-Park, Japan for the mu-SR measurement, and also I would like to thank the funding agencies for funding my research. Thank you for your attention.
Thank you, Professor. So, few small questions. Yeah, very interesting. So, is it spin liquid or you can't? Is this everything?
I can say up to 300 millikelvin the signatures are similar to that of a quantum spin liquid. But at 50 Kelvin, whether there is a ordering or there is no ordering, I cannot say. If there is a ordering, I cannot say it's a quantum spin liquid, but the behavior can be said as a spin liquid.
Single exponential decay.
Yes. Because if there is some, at least up to 300 millikelvin, we did not get any signature of any oscillations, or there is a drop in initial asymmetry and all those things.